This lecture is on quality control. I know you've done it before in other classes. There is no getting away from quality control in the laboratory. So we're just going to review these concepts, and then you're going to do some work to demonstrate that you know what you're supposed to be doing. So quality control in the laboratory can be divided into two broad areas, internal and external quality control. With internal quality control, it's where the majority of your work is being done in order to ensure that the tests that the procedures, I should say, that you're performing are actually performing as expected, and that there's no variation based on the day of the week or the reagents used or the technologist who's doing it. It ensures that everybody's doing what they're supposed to be doing at the same way. And so when we're talking about internal quality control, it's a lot of, it's kind of built into many of the instruments, but it's a lot of the math, calculating the mean, the standard deviation for any of the QC material that you're running. That allows you to test the precision and the accuracy of your test method or instrument, whatever the procedure is. If you run that QC material concurrently with your patient samples, then that allows you to ensure that the results that you're getting on that run is true. Okay, and some instruments or some procedures require that you run quality control with every test run. Other procedures the instruments or the procedures are designed in such a way that you only have to run the QC material maybe every few hundred patients or so. So it really depends on the procedure, the manufacturer, what they've determined, and also the fluctuation in the instrument itself. How much does the instrument change after each test run? Newer instruments allow you to run quality control less frequently because the instrument itself has a lot of built-in quality control. But depending on the procedure, you might have to run quality control material literally with every run. Okay, and then obviously if you're running it, then you also need to monitor the results. And monitoring the results not only in that particular run, but over time, allows you to notice if there have been changes either in the instrument or in the QC material that you're using. Or maybe there's a problem with the procedure itself. And you can detect, hopefully, this with the runs that you, with the monitoring that you perform in that procedure. One of the things that you have to make sure that you're doing is the idea of concurrent analysis. What that means is you can't run all of your quality control in the morning for the whole day and then start running your patients, theoretically. So the concurrent analysis means that quality control should be treated the same way as the patients. That means it's run just like materials are run for your patients. Okay, you don't run it separately. You don't do quality control in a different room with a different, you don't have a quality control tech who does all the quality control and everybody else runs the patients. That's not concurrent analysis, and it's not allowed. You do have to have a quality control tech assigned, but their job is the monitoring process. So monitoring quality control over a long period of time. This is especially important in the automated laboratories, chemistry in particular, but also hematology because you have the automated CBC. So you need to be able to monitor your quality control over a long period of time, week to day to month, to make sure that you're catching any systematic errors that might be occurring within the instrument, or maybe the quality control material is degrading, or maybe there's something that's changed with your processing systems. Can happen that maybe the centrifuge that you're using for a particular chemistry analyzer has deteriorated, and you're not getting full separation of the material, and so that changes your chemistry analysis. That's something that internal quality control should help you pick up. In addition to internal quality control, all labs are required to participate in external quality control. And external quality control allows you to compare the performance of your instruments, your methods, with other institutions that use the same instruments or methods. And it really, we say in your area, but it really could be anywhere. Now, you don't have the same patient samples, so you have to have some mechanism to compare the same sample across institutions. But you're still, the control for that is that you compare the same instruments or procedures. And probably the most common and most easily understood method of external quality control is proficiency testing. So laboratories purchase proficiency tests, whether it's from CAP or from the state that they are active in, and those tests are performed by every other organization that purchases those. So every CAP accredited laboratory purchases CAP proficiency exams, and those exams are sent to you semi-annually, and you usually twice a year, and you perform, let's say you get all the chemistry, so you perform all your chemistry testing on your instrument, and every other hospital that has that instrument will also perform those proficiency tests, and your results are compared to every other hospital. Now, the CAP knows what the results are, right? They performed the tests as well. So CAP, whoever provides proficiency material will know what the results should be, but we'll also compare the results that you get to every other institution that runs that analyzer or that procedure. And that allows you to compare how your instruments run. Even you can also perform a similar methodology, in particular when you have multiple instruments in the same hospital. So you might have an architect chemistry analyzer in the Gen Lab, in a Stat Lab, in a satellite lab. And you can compare how they're testing, how they're running within the same institution by splitting a sample and running it on all three analyzers. And that allows you to ensure, again, that your procedures are consistent throughout the entire institution. You don't want to have different results out of the Stat Lab that you do as compared to the Gen Lab. You need to make sure that those instruments run identically. And so splitting a sample and running it on all three machines, or whatever the case may be, in all areas, ensures that you get consistent results throughout the entire institution. Running proficiency testing ensures that you get consistent results across the field, but also that your institution is functioning at the same caliber as other institutions in the field. So we have to bring up all those math terms that relate to quality control. There's no getting around them. The key thing for running QC really is to ensure accuracy, precision, and reliability. Okay, we want to make sure that the tests that we run are accurate. So how close, remember what the definition of accuracy, how close does a result agree with the actual result? If CAP sends us a glucose and they know that they've sent us a glucose that is 98 grams per deciliter, and we are getting a result that is 99, then that's pretty good accuracy. That's a good measure of accuracy. We also have to measure precision. If we run that test 5 times and we get a result of 99, 99, and 98, and then what did I say, 5 times, and then 97, and then 99, that's relatively precise, very close distribution of results. We need to ensure that when we repeat tests, that we get pretty much the same result each time. We don't want results to be all over the place, because then how do you know which is the true result? And we use, in order to determine precision, we usually calculate standard deviation. So if you run all of your replicates and you calculate the standard deviation. The larger the standard deviation, the more imprecise the test is. So you want that standard deviation to approach really zero, okay, is the idea. Then we also perform all this math and keep track of all these things to ensure reliability. Reliability is a function of not just the accuracy, but also the precision, a combination of the two. And so by combining the two, accuracy and precision, together, then we can be assured that a particular test is reliable. If we have a very precise test, but not very accurate, that would be equivalent to having a very accurate test that's not very precise. We really would prefer to have the best we can of both issues. And you do have to, those numbers have to, the accuracy and the precision of a particular test has to be something that you document. You don't just rely on manufacturer's information. You have to demonstrate that you're performing the test close to or spot on for the accuracy and the precision that the manufacturer is reporting. Some other terms that will come up is, for example, central tendency. Central tendency is when you have a representation of a large group of data points that are equal to, or at least very nearly equal to, the same as one data point. So what you're saying is that to say that there is a central tendency for a particular test is what we're saying is that having, if we test 100 million, 100 million, that's a ridiculous number. If we test 1,000 patients at MSK, it would be this, we would get results that are about the same as any one individual patient. And some test results that we find, there is a very tight grouping as far as the results go. So you get this cluster of data points when you run it across an entire population. So when we're looking at the results, this would be associated with, for example, the test results that are maybe pos-neg, low pos. The central tendency would be on one side of a result or another. We don't look for a numeric distribution of results. With a numeric distribution of results, we're usually looking at normal or Gaussian distributions, where you have approximately the same number of results on either point of a peak. Okay, meaning there is a central peak there. The mean of the results should be obviously somewhere in the middle, and you'd have approximately the same number of results on either side of that mean. With a skewed distribution, however, we're looking at an asymmetrical spread of data points around a peak. So skewed distribution might refer to something that's physiologically limited. So for example, I don't know, something like this, let's talk about urinalysis. If you talk about the pH, say, of urine, well, there's a physiological limit. So you're not going to get a normal distribution. You're not necessarily going to get a central tendency because you're testing sick patients. So there, if you tested a broad range of healthy patients, you might get a central tendency towards a slightly acidic pH. You're definitely not going to get a normal distribution around a mean, okay? But with sick patients, you might get a skewed distribution towards highly acidic, especially maybe at Sloan Kettering with patients who are undergoing chemotherapy. That chemotherapy theoretically might change the pH of their urine to be slightly more acidic or slightly more basic, and so you might get a skewed distribution in that population. So knowing what how the data points for your population should be represented, sometimes it has to do with the nature of the result, the nature of what you're testing. some tests are positive or negative. Does the patient have flu or do they not have flu? Well, the central tendency would be for most patients to not have flu. Okay, most patients that you test are going to be negative for influenza. That's your central tendency. So then if you have somebody who differs from that, they become an abnormal, an outlier, somebody who's sick. Okay, makes sense. Normal or Gaussian distributions would apply a lot more to maybe our, the results that we're used to, our normal hemoglobin levels, our normal red cell counts, our normal chemistry results. They usually have some kind of Gaussian distribution. And then we have other things for which there is a physiological sort of endpoint. So specific gravity of urine or pH of urine. There's only so much that your kidneys can do, and it's usually a fairly tight range. So you usually don't get that Gaussian curve that you would associate with, say, glucose numbers or something like that. Okay. Now, to get those tendencies, to get those distributions, you need to know all of those factors that are on the left of this page. You need to know what the mean, the median, the mode, range, all of those things are. So you know what your mean is. That's your average, averageable data points. And I'm just giving you the mathematical formulas there. Thank God for PowerPoint, putting those in there. The median is the middle point of all your data, but remember that your data has to be given in numerical order for your median to be accurate. So don't put it in the order of the numbers tested. Put it in an ordering system from lowest to highest, and you'll take the middle data point at that point. Remember that if you have an even number of data points, that you average the two middle ones. Then you have your mode, which will be your most frequent number or value in a data set. And again, that might be important for certain test results that you get. Might be more accurate as far as what do we expect, what result do we expect for our patients, whereas the range is what can we expect, what's the possible results what are the possible results that are physiologically probable. Okay, and that's the difference between your high and your low values in a data set. So you know what the range is for a normal glucose result, for example. That gives you for normals, from say 90 to 110, if that's the normal for your chemistry range. But there are possibles outside that. You can see very, very high glucose levels. You can see very, very low glucose levels. Okay, so then you start asking, well, what's the most common result that we might get? And that might be for a particular patient, or it might be for a particular population. So what's common for, say, a group of diabetics? Well, yes, we'd like to see, a fasting glucose of 95. That sounds fabulous. But is that something that's typical for diabetics? Do we normally get a 95 fasting on diabetics? Or is a 120, 125 fasting something that we would say, oh, I'd be okay with that if it's a diabetic. So these numbers are all different based on the population that you're applying them to. Now, once you have the mean, median, mode, and range, then you start looking at things like variance, standard deviation, all of those things to help you determine the QC, how the quality control of particular runs and such. The variance, it refers to the dispersion or the degree of tightness of a particular set of data points, in particular around the mean. Okay, so basically the variance is equal to the square root of the square of the standard deviation. You can see the standard deviation is there, and you just square it, and you end up with the variance. Standard deviation is something that is vital in the laboratory because we base our range upon the standard deviations of particular data sets. This will represent the standard deviation, will represent the dispersion of the data points around the mean itself. And this is equal to the square root of the variance. So the variance and the standard deviation are both related to each other. One's the square root of the other. The standard deviation is the one that we use more commonly, because if you have 2 standard deviations from the mean, you're encompassing 96% of the population, the normal population. So standard deviation is something that we use in the laboratory significantly. We also see standard deviations to help us, we use standard deviations to help us predict the possible range, the possible change from one specimen to another on the same patient. So, for example, when we're looking at a result on a patient that's taken at 8 o'clock in the morning and a result that's taken maybe 5 or 6 hours later on the same patient, they're considered the same if they are within 2 standard deviation of each other, those results. So they're considered unchanged. When those 2 results start to change more than 2 standard deviations, you have to start thinking that either something has physiologically changed in the patient or it's not the same specimen. These are the kind of things that we're looking at when we try to compare. You have a specimen in a tube. How do you know for sure that it actually came from the same patient? And how do you know that it represents a physiological change in the patient? The numbers are not going to be the same from 9 o'clock in the morning to 3 o'clock in the afternoon. They're not likely to be the same. So if they're not the same, when do we know that it means that there's been some kind of physiological change? Well, one of the mechanisms that we use is by comparing those. How many standard deviation are they away from each other? And usually if they're within 2, it's considered the same. So if you had a panic result at 9 o'clock in the morning, you had to call up to the floor. They repeat the same test 3 o'clock in the afternoon, and it's still panic, and it's this, but it's 2 standard. It's less than 2 standard deviation away from the 9 a.m. It's probably still the same physiologic problem going on. Then we have confidence intervals. These refer to the limits, the high and low values between which a specific proportion of the data points in any particular data set will fall. So this is what we were talking about when we say that if you go 2 standard deviation, you're at almost 96% of the population. So one standard deviation from the mean, plus or minus, will contain 68% of the population or of the data points. 2 standard deviations is actually 95%, and then 3 standard deviations is 99%. One of the things you want to point out here is that you're never going to capture, it's not possible, because if you remember that Gaussian distribution, it's a gradually sloping curve, so you're not going to capture 100% of the data points. And trust me, you always can find some really weird numbers that you'll get out of your patients. One of the big things to remember is they're not normal, they're sick, so you can get some really funky things. And then finally, we have coefficient of variation. Coefficient of variation is highly useful, in particular when you're comparing different procedures to each other. So the formula, standard deviation is divided by the mean and then multiplied by 100 to express it as percentage. And basically, when you're looking at coefficient of variation, it allows you to compare 2 different methods of analysis, which both methods will probably have very different means because they're not the same method. And so you want to determine, well, I have these 2 different methods that I could use to perform glucose, for example. The mean on this method is, say, 98. The mean on this other method over here is 95. 2 different means. Well, how can I determine if how much variation there is between these 2? So coefficient of variation allows you to compare these two. And if you get a number that is less than 5% for the coefficient of variation, that's what we're looking for acceptable variation between two different procedures. Now you're going to do all that math, and then you're going to take that math and you're going to analyze, or somebody's going to analyze that math. Now, as far as you're concerned, QC at the very least is those specimen, those control material that you have to run with every time you run the procedure. And also recording that QC material. And it's not just the QC material, it's all the other things that you run around doing, writing down the temperatures, washing the benches, and double checking your instruments for your preventive maintenance, all of those things. That's all part of your QC to ensure that your instrument is running properly. Analysis of the data, as a general rule, we like to use Levy-Jennings charts because they are so they're such good representations of what's going on over a period of time for a particular test. And so we use these Levy-Jennings charts to monitor any particular method over a long time for performance, and allows us to assess precision and long-term accuracy. Not accuracy on any one particular day, but long-term accuracy. And the charts are going to be graphs, and the x-axis is time, and the y-axis is standard deviation values, 1, 2, and 3 standard deviation values from whatever the mean on that particular control material is. So remember, you have a Levy-Jennings chart set up for each test, and you have a different line for each individual control material. So you have, if we stick with glucose, you have your glucose low, you have your glucose normal, and then you have your glucose high material if you run 3 QCs. And you chart each of them on their own, with their own separate line on a Levy-Jennings chart. Each one will have a different mean, right? Because your low material will have a mean, an expected result, mean expected, and then your normal will have its own expected. And so you need different charts for each one. And what these charts allow you to do in a pictorial sense is allow you to spot trends and shifts that might be occurring with your procedure. Okay, and so this chart that's here, this little picture that we see here, gives you a schematic to determine can I accept the run, or do I have to retest something. In the very first thing you're going to do is, did your control material work? If your control material is within 2 standard deviations, then you're fine. It's fine. Okay, you're not going to hit the same exact number every day. We know that. So if it is within those, less than 2 standard deviations, you're fine. Keep running it. You can see here, if it's not outside 2 standard deviations, you accept the run and report the results. No big deal. If, however, it's greater than 2 standard deviations, you start moving down this line here, and you try and see, well, which things do I have to do before I report the results on this run. And remember, this is going to apply to each one of your controls that you run, not just one of them. Okay, so and I don't need to read this whole thing to you. You can see what they're giving you are the Westgard rules here. You've heard of them before. The 1-2S is one result, 2 standard deviations. 1-3S, 1 result, 3 standard deviations, and so on down the line. And what this allows you to detect are trends. For example, a trend will be a small but steady and continuous change in any one direction. Usually when you have a trend occurring where your QC is gradually getting higher and higher, or lower and lower away from the mean, usually that indicates some kind of maybe reagent or calibrator deterioration. It could also mean something's going on with the instrument. So, for example, maybe dust is building up on a lens somewhere, and that needs to be cleaned, those kind of things. Maybe it hasn't been cleaned because technologist X, who never likes to clean that lens, is running it this whole week, and so it's gradually getting dirtier throughout the week. These are all things that are possibilities, and I've seen them happen. Okay. So with a trend, you're going to start usually the things like when you have four, you get these 4 results always on one side of the mean, those kind of things. You start looking for, wait a minute, something's going on. You also can detect shifts. Shifts are when you have a complete change of the mean for the control material, with the new mean being continuous or but different from the original mean. Usually, there's some flaw in the instrument in this case. A new mean should not come from deteriorated quality control, not when it's continuously new. So there's probably been some consistent flaw in the instrument or change. Potentially, one of the other things that could happen is you did have a lot change in the control, but you never changed the lot inside the instrument. That's one of the things that these newer instruments require, that you update the lots within the instrument, and if you don't do that, you'll probably see a shift in the results that you get. As a general, as a good rule, I should say, a commonly accepted rule, 95% CI rule. This is a commonly accepted rule within the laboratory, that the control values should fall within 2 standard deviation for the analysis to be accepted and the patient results to be reported out. And that 95% confidence rule, that is what we're talking about when we talk about a single patient result to the next patient, same patient result. So it is difficult for you to physiologically explain a result that is outside of 2 standard deviations from a previous result. Remember, our patients are sick, so they're not necessarily always going to be normal. So if I get a glucose value at 9 o'clock in the morning of 90, that's still within normal, so that's fine. But then 3 hours later, I end up with a glucose value of 200. That's well outside of the 2 standard deviation rule. Those 2 specimens do not match each other over 3 hours time. You have to explain that 95% confidence rule. You have to explain that. It's called a delta fail before you report those results. Generally speaking, the first thing you're going to do is repeat that test. You're going to check your patient identifiers on your tubes, and you're going to repeat that test. The best practice would be to repeat both of those tests. Go back to that original 9 o'clock specimen and rerun it. Check your identifiers on that, and then check the identifiers on the second test and rerun that. If you get the same kind of difference, then I would suggest that there might be a difference in the patient itself. Somebody drew the wrong sample potentially. So collecting another specimen off of that patient might be a good idea. The Westgard rules are the rules, you've heard of them before, that we use, that we set up to analyze these Levy-Jennings charts, and they allow us to determine if a problem is present, if it's a random problem or a systematic problem. The R4S and 1,3S rules, those are usually random error rules, whereas the 2,2S, 4,1S, and 10X rules, those are usually systemic errors. The random error would be, what that's defined as, is any error occurring on a unique sample, on an individual sample, without, there's no pattern involved in it. Usually you can resolve a random error. Just repeat the assay. Okay, just do it over again and the error will disappear. It could be a result of maybe technologist error, pipetting error. It could be any number of random things that would have affected any other sample as equally as this sample. So it doesn't represent a true result. A systematic error, however, systematic error represents error that is present in all the samples in a particular run and affects all the samples approximately equally. a systematic error can be either a trend or a shift, and it can't be resolved by repeating the assay. So it doesn't go away just by running it again. You need to find out what the problem is. Usually it would be within the, although it could, usually it would be within the instrument if it's affecting all of the samples equally. Could be a reagent issue, could be any number of issues going on. This chart here, the only thing that this is showing you is basically it's a flow chart for a particular laboratory to demonstrate what you should do when the controls are out of range for a particular instrument. So these flow charts are perfectly legitimate. You can have them. These are not allowed to replace your procedures, but many hospitals, laboratories, they like to have these flow charts because they find them easier to read than an entire procedure to figure out what you should do, and because there's so many things that could go wrong. Okay, so you can see, as with most hospitals, if your controls are out of range, usually the first thing that you're going to do is repeat the controls. So and then repeating the controls, I just want to point out something here, that repeating the controls is acceptable, but that's not, the corrective action has not necessarily been taken yet. So you still have a little bit more than just repeating the controls, and you can't ignore the fact that you had an outlier. Okay, so you have to mark that as an outlier, as a random error, and that's your corrective action. If the repeat did not fix the out of control issue, you're going to start doing things like check your expiration dates. Truthfully, if you don't check your expiration dates first, I don't know what's wrong with you, because then you just wasted a run. So check your expiration dates before you start repeating the controls of all your reagents and all your control material, because then you'd at least be able to explain. In some parts of the lab, if you get 3 fails, it really starts causing a lot of problems. In microbiology, it does anyway. It starts causing a lot of problems. We have to start doing things for 30 days. So don't waste a run. Okay, make sure that you check your expiration dates before you run things the second time. But you can see this is instrument specific, so you can see that there's procedures that they're following as far as removing, flexing, and reloading, all of these things, thawing fresh bottles and all that stuff. These flowcharts are perfectly legitimate. They're allowed to be posted near the instrument for a procedure for when results are out of range. However, they do not replace a written out procedure in the proper format, and they must be included. If you are going to use them, they must be included in the procedure. So this is just a portion of the procedure, and you have to have a full written version of this in order to use them. Here's your Levy-Jennings graphs. I know you guys love these. I'm sure you did lots of them with Lauren in laboratory. And you can see all it is, it's actually pretty simple. You have your mean at the center here, and then you go one standard deviation, 2 standard deviations away in both directions, +1, -1, -2. Okay, so you go down there. And what you're looking for normal results, you want to see the material bouncing on both sides of the mean, up and down, back and forth. You don't want it to always stay on one side of the mean. What you're looking for are things that are outside. So you have an obvious fail here, greater than 2, standard deviation away. You have a problem there that would have had to have been addressed. An inspector who comes in will ask, okay, I want to see these results, these incidents that happened around the 30th day, looks like maybe the 28th and the 31st or 2nd day of your QC material, and I want to see what was done. Now, I'm saying days. These could be runs. In some instruments, you'll run QC more than once a day. So these might be runs. This could be, you know, morning, afternoon, evening, night, and you can go on and on, okay? This is another Levy-Jennings chart, just looking at, you know, they didn't put in numbers over here. They just literally have the plus and minus 1 and 2 standard deviations, and then the number of runs on the bottom. Could be runs, could be days, doesn't really matter. And again, what you're looking for the most part is that it bounces back and forth across the mean. And here's your mean at 0. So again, what are we looking for? These outliers here, they're plus or minus, they're before 1 or more, more than 2 standard deviation on either side. Those ones obviously have to be explained. And on those days, there better be a result entry to explain why that failed. Okay, random error, systematic error, and what your corrective action was. Then you also have to look for the trends and shifts that exist within the material. So this one doesn't look too bad. You're looking for, you know, you have some trends and shifts up here. These are all on the same side of the mean. Why are they all on the same side of the mean? It might represent a new a shift that's occurred in the QC material. Here's another group here that's all on this. Oops, well, that didn't count. I meant to make that circle smaller. All on the same side of the mean. Why are there so many on the same side of the mean? We don't like to see that. You have 1, 2, 3, 4, 5. All those runs on the same side of the mean. We need to check our reagents and make sure that they're within date and not deteriorated, storage properly. When you have something like this, the inspector could come to you and say, you know what, I'd like to see the temperature logs for your storage refrigerator and make sure the temperature logs were okay, because this kind of looks like maybe they weren't okay. I'd like to see the QC dates. These are all things that the inspector might note, and these might also help to explain why the QC material did deteriorate. Now, probably one of the things that becomes it is outlined by JCAHO, the frequency of QC testing, but many hospitals increase the number of QC testing because it helps them to catch those errors. There are a minimum number of assays that have to be performed. There is a minimum of 2 controls that are required, and the current guidelines require that those 2 controls be run at least once per day or shift as it applies. So if the procedure is only performed on 1 shift, then you have to run that QC once per shift. That's the minimum guidelines. If that procedure is only run on, say, the day shift, then you only have to run it once per day. If it is run on every shift, it does have to be run once per shift. That's the minimum, but most hospitals do it a little bit more than that. And the reason, as you can see by this chart over here, the reason for that, if you look at figure 1A, Lab A examines 50 patients every day and does 1 QC evaluation every 24 hours. That means if you look at the green diamonds, that's their QC. That's when they perform QC. So this is when it is performed. So how many, if there is a malfunction, if you look now at figure 2, if we add into this data up here, if we add into figure 1, just the number of tests run and the number of times QC is performed, Lab A could have a malfunction halfway through the day, and it will not be detected until the next QC is performed. That means all of these specimens, whoops, pardon my terrible lines, have to be rerun because of the malfunction. We know that none of these are working properly, but in reality, you're going to have to run all of them because you have to go back to the last time QC worked, okay? In Lab B, it becomes even more because they run so many more specimens. Look at all, they have to go back to the last time QC worked, and they have to run all of those 300 patients over again. In Lab C, because they run, although less patients than Lab B, they perform QC every 8 hours. So when a malfunction occurs at the same time, they only need to go back to when they last performed QC and rerun these patients over again. That allows them to ensure that they're really covering themselves. So they don't have to rerun every single patient. When you have a QC failure, you assume that everything that was run from the last time QC worked is suspect, and you need to repeat them. So when you perform a lot of tests, consider adding a lot of QC. Okay? Because then you would have to reperform a lot less of those tests when you do have a malfunction. And basically what that does is it minimizes patient risk. Okay? It minimizes costs as well. Okay?